How do the application shortcomings of these materials manifest during battery operation? And what specific challenges are encountered, such as limitations in rate performance or stability issues over prolonged cycling? What are the underlying factors driving these shortcomings, and how might they be correlated with the inherent structural or electronic properties of the P2 type, O3 type, and tunnel type oxides? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? How can the modification process be tailored to mitigate these limitations? And what synthesis strategies or doping methods have been explored to optimize the sodium storage capabilities while enhancing structural stability and electrochemical performance? What roles do experimental conditions and process variations play in modifying the crystal structure and transforming the cases where the materials might exhibit suboptimal performance into systems with improved efficiency and operational lifespan? How does a thorough analysis of both the sodium storage mechanism and these modification processes enable researchers to better predict the practical application prospects of these materials for next-generation sodium-ion batteries? And in what ways might these insights guide future material design and innovation in the field? What are the implications of the low energy density of sodium-ion batteries for their use in large-scale energy storage applications? And how does this limitation drive efforts to reduce production costs in order to maintain market competitiveness against other energy storage devices? How does the inherently low price of iron-based compounds influence the research focus on O3 type transition metal oxides? And in what ways do iron-based materials provide a cost-effective advantage when developing and scaling sodium-ion battery components? What makes alpha NaFeO2 a typical and representative example of O3 type layered transition metal oxides, and how do its structural and chemical characteristics contribute to its effectiveness in sodium storage? How can the synthesis process of alpha NaFeO2 achieved through a simple solid-state reaction between sodium peroxide, Na2O2, and iron oxides such as Fe2O3 or Fe3O4 under air calcination conditions be optimized? And which specific reaction parameters ensure the formation of a pure, high-performance layered structure? In what ways do the low cost of raw materials and the minimal production requirements bolster the practical and economic appeal of the synthesis method? And how might these factors create a competitive edge for sodium-ion batteries in large-scale energy applications? What role did the early work, such as the by Okada et al., play in introducing and validating the sodium storage properties of O3 type alpha NaFeO2? And how does the confirmation of its XRD pattern serve as evidence for the successful synthesis and structural integrity of the material? What?